Snowboarding is an exhilarating and high-action winter sport that many people love and participate in annually. Since its creation, the advancement of this sport can be related to various physics principles.
In this case, we'll be focusing on a video of Kyle, a snowboarding instructor at Glen Eden who builds and tests park features, testing a ramp of 25 degrees, distance 3 meters, and performing a 360 rotation over a 7-meter gap that he constructed to analyze such concepts from motion to elastic potential energy. Let's first start with the motion that the boarder takes leading up to becoming a projectile. We can calculate the initial velocity that the boarder is traveling. Knowing that there's 30 frames per second, we can divide 1 second by the amount of frames, 30, to give us 0.033 seconds per frame. With this information, we can multiply the amount of frames it took to travel up the ramp, or shall I say inclined plane. This ends up being 13 frames, giving us a time of 0.43 seconds. Last but not least, we solve for the initial velocity by dividing 3 meters by 0.43 seconds, to give us 7.0 meters per second. Now with this velocity, we can determine the maximum height during his projectile motion. For this, we must find the initial velocity in the y direction, 3.0 meters per second. With this value, we now can calculate the maximum height using the smallest of the big five. After setting the final velocity to 0, we get the height of 0.46 meters, but this doesn't give us our max height above the ground. For this, we must find the height of the jump using trigonometry, which is 1.3 meters, giving us a maximum height after addition of 1.8 meters. Wow! Moving on to the landing, we use the biggest of the big five to calculate the total time of flight. After subbing and using concepts of equivalent proportions of the height of the incline and decline planes, we get the values to a quadratic equation. We straight away utilize the quadratic formula to give us a total flight time of 1.1 seconds. Once with this asset of time, we work out the velocity of which the boarder lands, using the smallest of the big five once again to find the final velocity in the y direction, which is 14 meters per second. With this, we can discover final velocity. Knowing that the final velocity in the x direction will be equal in magnitude to its initial velocity, we can use pi-gram theorem to get 15 meters per second. And to complete this, we must give its angle below the horizontal, which ends up being 24 degrees, which is just a degree shy of its angle above horizontal. Not all jumps are made equal.
Now we will be focusing on vertical circular motion from the movement of the snowboarder during his acceleration up the ramp. Once we have a free body diagram sketched, we see that the position of the boarder is on our incline with an angle of 25 degrees, which will provide a force of gravity down and a normal force perpendicular to the plane with an x and y component. From this diagram, we can see that Fnx is responsible for the centripetal acceleration. After calculating the radius of the ramp with its hypotenuse and knowing the boarder's velocity, we can use the formula AC equals v squared over r. The result is a centripetal acceleration of 18 meters per second squared. Using this information and the mass of the rider, we can solve for the centripetal force using Fc equals mac. As a result, the rider is traveling with a force of 1.2 times 10 to the 3 newtons around the ramp. Looking further, we can analyze the 360-degree spin. By drawing a sketch of the scenario, there is a force of gravity from the earth, a normal force from the snowboard, and an action-reaction force between the rider's feet and the bindings. This creates the following free body diagram, which shows that the centripetal acceleration is caused by the action-reaction force. In order to solve for the centripetal force, we must solve for the velocity of the board during the spin. This can be done by finding the period of the rotation, as the video is in 30 frames per second, and counting 29 frames, which provides a period of 0.9 seconds. Now using velocity equals 2 pi r over t, we can use the radius of the snowboard and the period to solve for the velocity, which is 5 meters per second. With this information, we can use the formula Fc equals Fnet equals mac, and after subbing in the values, we see that there is a centripetal force of 2.2 times 10 to the 3 newtons, which allows a rider to complete the spin. Another factor in the rider's jump is a change in gravitational potential energy. This must be calculated as a change in energy that is too great will result in injuries or broken bones. The following sketch represents where I will be calculating Eg1 and Eg2 to find the change in gravitational potential energy. With the reference point as a ground, Eg1 is calculated using the formula Eg equals mg times the delta y. And with a height of 1.3 meters and a mass of 68 kilograms gravity, we can find that Eg1 is equal to 8.7 times 10 to the 2 joules. EG2 is calculated using the landing point, which is 1.3 meters below the reference point, which provides a value of negative 8.7 times 10 to the 2 joules. Now to solve for the change in gravitational potential energy, we subtract Eg1 from Eg2, showing that delta Eg is equal to negative 1.7 times 10 to the 3 joules. Comparing this to the Scientific American Journal, which says it can take up to 9,920 joules of energy to break a bone, our rider should be able to land safely.
Now let's figure out the spring potential energy for the boarder's ability to pop his trick into the air. With the formulas for the spring's potential energy and force, we can solve for the total spring potential energy and the stiffness of the board. Drawing a free body diagram of the board fully stretched out at rest, F net is equal to the force of the spring minus the force of gravity. Rearranging the formula for K using the value of mass, gravity, and delta x, the constant force needed to compress the board is 1.3 times 10 to the 4 newton meters. 3 times 10 to the 4 newton meters.
With the constant value, we can calculate the spring potential energy of the board when it is stretched to 0.05 meters from its equilibrium position. By subbing in the K and X values, the spring potential energy in the board is 16 joules. This high value of stiffness and low spring potential energy is important to riders who perform difficult tricks and maneuvers as seen in the video.